Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're very happy to have here Moshe Tenenholz from the Technion. He's visiting us for 2 days, so if you want to speak to him, he'll be here today and tomorrow. And he'll talk about an axiomatic approach to ranking systems.
Thank you. So a short introduction here is that I've been working on issues related to the interface between computer science and artificial intelligence, in particular to issues in the social sciences and game theory for many, many years. And I didn't know exactly what kind of topic to choose here, so I chose some survey, but if not that big survey that will be able to also tell you some results. And I've chosen to look at something that we have been looking in the last 3 years or so, and most of the work presented in this talk is a joint work with my student, Alon Altman. So we'll talk about ranking systems. And again, I try to give you the basic conceptual things with many, many results. And I'm here for 2 days to dig with you many of these results. Perhaps I'll give a hint of proof or something like that that will show, also see some of the depth. So basically, what are ranking systems? There are systems in which agents rank for each other, and these ranks are aggregated into a social ranking. So basically, we'll see examples, but basically they are systems where there's a bunch of agents, where these agents say something about other agents, and at the end, you should aggregate all of this into some social ranking. They can be defined in terms of a ranking function that combines the individual votes of agents into a social ranking of the agents. So from a theory perspective, what is of interest here is that this is basically an extension or variation of the classical theory of social choice, a very celebrated theory with its own Nobel Prizes, where the mathematical change is that we have the set of agents and a set of alternatives coincide. And this gives us a lot of interesting kind of theory to build, and it's immediately become applicable suddenly to things which are very, very hot today, such as page ranking, reputation systems, and stuff like that. So what I'd like to convey to you today is something which is a new theory, which also had, surprisingly, at least for me, some quite immediate applications. Also, I'd like to sell to you here today something that is called the axiomatic approach to ranking systems that there's another message that I'd like to bring to you. So what is social choice? Again, I assume that the background is people have math background, but I don't know, in addition, what they know. So the classical social choice setting, roughly speaking, is the following one. This is arrow setting, fundamental setting. You have a bunch of agents or voters, and there is a set of alternatives, like you have in elections, and a preference relation for each agent over the set of alternatives. And the whole idea is to take the individual agent's preferences and to aggregate them into a social preference. So a social welfare function is a mapping between the agent's individual preferences into a social ranking over the alternatives. So it's a very, very fundamental kind of setting. And one can ask, what will be a good aggregation rule? Or study the properties of existing aggregation rules, such as majority rules that we use in our everyday life. So we'd like to produce good social welfare function. That's the classical setting with zillions of papers and prizes and whatever. So what is our, first of all, an example to something we didn't see. So it's a nice animation due to Alon. So we have here a bunch of guys with a preference relation. There can be, of course, in the same order, and we need to aggregate them into a social ranking. So this is the classical picture. Again, fine? So let's continue. We move and do the following patch. Voters and alternatives are the same set. So they'll be called in different names depending on application. They can be called agents. They can be called pages. And what we have here, in fact, in this talk, I've chosen to concentrate in something which we call graph ranking systems, which says it's not just that they are the same set. Each agent may only make binary votes, only specify some subset of the agents as good. So this is a graph. Basically, the edges point to the agents that you prefer. You are a node in this graph.
It's a diagram, a
Yeah, a directed graph. And basically each node, we interpret this graph as a bunch of voters, which are also a bunch of alternatives. And each voter has a preference among the other voters, which is, and therefore, the vote, this two-level kind of thing, dichotomous preferences, those that you prefer upon the other ones. So, and immediately when you make this interpretation, what becomes now the problem of aggregation? For example, if you're a Googler, then it means this is exactly the problem of page ranking. What do you do there? It's just, you say, let's call each agent a page. Let the page point link to one another. And this is the importance relation that we speak about. And basically now to aggregate this into a social preference, it's just decide on the page ranking. If you are an eBay guy and you talk about reputation, it will be the same thing. If you're in trust system, it will be the same thing. So it makes it applicable to this kind of setting.
So it doesn't cover personalization.
We'll talk about personalization. It will be a big topic. But it'll be, yeah, we'll talk about, we have very strong result for personalization. This is global ranking, and we'll talk about personalized ranking system, large part of this talk. But there are many, it's a whole new area of research. But thanks for the question. So the picture now is like that. Okay? We have this graph, and you like to create this page ranking. So again, there are zillions, not zillions, 5 papers that we can look at. For me, the zillions is too much. And everything is defined formally, and we can talk about this, but I'd like to keep the intuition. Formally, a graph ranking system defined as a functional, it's not a function, it's a functional. From the set of all graphs to the set of linear orderings on the vertices. This may be partial function, but we understand the intuition. And at the end, you get a graph, and you need to rank these vertices, which will be the ordering. So what is the axiomatic approach? Again, to those of you that come from the social sciences, the mathematical social sciences, I don't need to sell it, but for many others, I need to sell it. So what we'd like to do, we'd like to know what is a good aggregation rule. Or we'd like to know whether a particular aggregation rule, we have now a very famous one, PageRank, is good or not. So the idea is to use what we call the axiomatic approach, or representation theorems in mathematical terms. The idea is we introduce a bunch of properties that we call axioms, and we do them with them two kinds of things. One of them is a normative approach. In a sense, we say, look, what we'd like to have is this property and this property and this property. We'd like that we have, if a system ranks A better than B, and now there is a new guy that points to A and didn't point to B, then A should be still stronger than B. Certain obvious properties. And the magic of the normative approach is that we, based on these properties, we try to say whether there exists a system that satisfies all of them. Perhaps there is a possibility result. Perhaps there is a possibility result. The descriptive approach is complementary. You say, look, there is a very powerful existing ranking system. So in our everyday lives, there are majority rules, there are plurality rules. Are they good or bad? And we can start with certain requirements and see that they fully characterize this system. And in fact, you will see this in ranking systems. So the idea here is this is something that is really, really deep and give foundations to social sciences. What we'd like is to bring this into the idea of ranking systems, where the set of agents and set of voters coincide. And I'll return, of course, to this point later. Now it's at least, I'm waving my hands because I've never seen an axiom. So we apply both to ranking system, similar to seminal studies as a classical social choice setting. Again, to those of you that are familiar, the basis to error Nobel Prize is error impossibility theorem. It's the most basic result in the normative approach. We start with a certain set of simple axioms, and then errors show that it's impossible, basically, to satisfy these axioms, or that any social system that satisfies them must be a dictator. You must have a dictator. Nice results like that. But this doesn't apply to ranking system because the ranking system has many, many other features. Or another example is people look at the majority rule and try to give axiomatization for that one. And we don't care that much about majority rule because this is not something that will help us in page ranking or in reputation systems. But there are already very strong things that people really use. In fact, all of the companies use in order to in fact, rank pages, such as the PageRank algorithm. And therefore, we'll try to understand this. So what is the plan of this talk? I'll touch very briefly on that, but this is a plan for these 2 days. I was hoping that people will be interested. That's the classical setting. Social choice, error, it's not ours. We didn't get the Nobel Prize. Now, there is an extension of this classical setting to deal with incentives, with the fact that people can cheat. Those of you that heard the mechanism design and stuff like that, this talks about that. The fundamental theorem there is Gibart-Satterwhite theorem. And we talk about the Kosovo social choice because these are graph ranking systems where there are 2 levels of preference. So that's the classical kind of thing. What we introduce is the study of ranking systems. And what I've chosen is just to tell you some results. So here we hit, immediately in the beginning of the talk, the PageRank. We like to say, OK, use PageRank. Use, it means Google, Yahoo, Microsoft. And basically, PageRank is just random walk. And does this make sense? Random walk is computation in linear algebra. Does it make sense as an aggregation rule? So we'll start with that as an example of the descriptive approach. Then we'll talk about the axiomatic approach, normative approach. So who should care about just PageRank? Let's start from a set of axioms and see whether we can build the optimal, ultimate ranking system. I'll skip this because you heard too much mechanism design. But these are incentive compatible ranking systems. So I'll talk about this, and there are 2 papers written on that I can talk about this. And for Yossi request, I'll talk about personalized ranking system, which is important to issue of such trust systems, such as shopping.com, stuff like that. People like to rank trust system, PGP. People like to rank the agents for the perspective of a particular agent and not have something global. So that's the plan. OK, so this was a joke that I'll skip. There are various kind of interesting kind of rankings. But we'll talk about PageRank, and this audience, I guess, will be a simplified version, which is just random walk, but I'll call it PageRank in order to be popular. So you all know random walk. Basically, we rank according to the statutory probabilities of a random walk. So just formally, you are given a graph. We assume that it's strongly connected for this talk in order not to deal with patches. We assume it's strongly connected. And so we basically look at this matrix, which is a standard matrix. In the entry ij, we have 1 over the cardinality of the successor set of node j. And this random walk is just looking at the principal eigenvector of the matrix A. Or if you wish, you just start with the random page, look at the outgoing links. In uniform distribution, choose one of these links. Go ahead, look at the limit. And this gives you some distribution of the pages that you can be. And the observation by Navin and Pinsky, now associated for some reason with other guys, is that this is a good measure. This is the way that we make impact ratio of journals and stuff like that. And what we have here is basically that the probability that you reach a particular page is the way that you define your preference among these guys. So what do you mean by that?
So rather than having the jump every 7th step, you just assume it's strongly connected, so you're not going to get.
Yeah, in fact, it's not naive assumption, to be truthful. So in a sense,
because it's not. I mean, the web, for example, is not.
No. And this is solved by companies by having what is called damping factor, with some probability, small probability, you jump to a random page. And this makes some complications that I don't like to get into. So they make it strongly connected by having some, any 2 states communicating, but I don't like to get into this. So I start with strongly connected. I can tell you, OK? Just in order to have a clean kind of setting. So, but the important thing is that basically you say that page A is preferable, or at least preferable at page B, if the probability of reaching in a random walk, page A, is greater or equal to the probability of reaching to page B. That's the whole idea behind this kind of ranking algorithms. So what we mean now by representation theorem, or in fact, I kill all of the excitement by saying a representation theorem, but the idea is try to understand whether this makes sense. Whether we'd like to look at properties of this. All of this is computation, linear algebra. So I'd like to look at certain properties of this and try to see whether they make sense. What do I mean by make sense? I'll write to you down several properties, which will be, the important thing is graph theoretical ordinal properties. Not whole computations or whatever, that will turn out to be properties of random walk. Very simple properties. The magic that we'd like to show is, can you connect these properties at end to this computation of principal eigenvectors? So I'd not like to kill the excitement, but the idea will be, it will be very nice if I can come with 5 properties. I'm not saying that we are achieving this. 5 properties such that are simple properties of PageRank, of random walk, which are completely ordinal, no numerical computations. And at end, it turns out that not just it satisfies that, but that every system that satisfies them must be PageRank. So this will be connect the graph theoretic ordinal things to this linear algebra kind of thing, and also explain us exactly what is the essence of PageRank. Is it clear where I'm going?
But you could have some other set of axioms that would also imply.
Right, that's the truth, but they will be equivalent exactly to these axioms.
Yeah.
The only thing here is this should be graph theoretical ordinal axioms. By the way, the reason I mention it, there are very famous people that already, in parallel to us basically, published the metric kind of results that are not ordinal graph theoretics. We need to be very careful with this because at the end, the simplest axiomatization is what? Just say, compute the principal eigenvectors and do that. It will be naive. But we need to be very careful here. So here are some axioms. Again, it's just to warm up So one of them, in fact, for computer scientists, different notions than to social scientists. So this is just the isomorphism requirement. It just says that the ranking system should be insensitive or to the renaming of the agents. So if you change the name of the agents, this shouldn't change the ranking of the agents, just change the name, okay? That's obvious. The names doesn't play a major role. So what will be a second requirement? Here is a requirement that I've chosen to quote it in a more arguable way, although it can be, again, relaxed. It is, and PageRank satisfy it. This axiom states that adding a self-edge on a node V strengthens this node, but doesn't change the relative ranking of other vertices. So this makes a lot of sense unless you'd like to say, let's remove self-edges. Self-edges doesn't make sense. And I'll skip this point. We can do everything with all self-edges. Such a requirement will be just, if there is additional agent that you point to it and it points back, then it will strengthen that agent. So we can do with all self-edges, but in order not to kill the presentation that much, then I just have this kind of naive kind of thing.
Do you have a multigraph, so multiple edges from one to the other, or not?
So,
From one agent.
Yeah. It's an arbitrarily directed graph.
You could kill the self-edges, and you could kill the multiple edges and just say simple graphs. But I'm wondering whether you have
I can have multiple edges. Okay. Or in fact, I can also deal without multiple edges. You can take both, in a sense. Let's assume for simplicity you don't have even multiple edges, if it helps to make things clear. So self-edges is just in fact that is common to practitioners, in a sense. There are systems that assume that are allowed self-edges, just as Google kind of things, and there are people that don't assume that. That it will not change the assumption. It will be very slightly different. You just say, if you don't allow self-edges, the axioms will say, if you add one more agent you point to and it point back, then you strengthen yourself. By the way, it starts to be a bit more tricky, but still not that bad. Vote by committee axiom captures the fact that an agent may vote indirectly via as many number of intermediate agents, each of which vote to the same original preferences. It doesn't change the relative rank of the agents. Something very simple. I think picture says everything. So if A voted to B and C, A can split itself to 3 voters that will vote exactly the same. Still, this shouldn't change the relative rank of A, B, and C. Of course, there are new agents here, and they may be ranked similar in particular way, but A, B, and C the rank should be the same.
Now, of course, in practice, when I think about some ranking systems, people do split themselves and hide the fact that they split themselves, and it does change the rank.
So we'll talk about this, but the problem of the key point is that online, you talk about the siblings problem, but even before that, we just talk about now random walk. In a sense, you have a random walk. This is property of random walk. Now you touched on incentives, on the idea whether this is the right graph. We'll get into it. We try to separate all of these issues. We are now in social choice kind of setting. So is it clear? Is it fine? The other axiom now is collapsing. Still makes sense. The collapsing axiom captures the fact that voters which have the same preferences may be collapsed to a single voter with the same preferences, voted by all of the voters for both. Where, of course, we need to assume that the voter sets for the collapsed vertices are disjoint. So if A and B votes have the same successor set, you can just take the union of that, let them all point to A, and let A point to the successor set, and you'll get the same kind of ranking of all vertices, excluding, of course, A and B. And the last one, by the way, which is, there's a side issue, that side remark that I give to theoreticians, which is the most arguable one, to people that like PageRank, but I say this is the proxy axiom that says, the proxy axiom captures the fact that n voters of equal rank were voted through a proxy, through X, to n alternatives, can achieve the same result by directly voting in a one-to-one fashion, like that, without having this proxy in the middle. So this is a property of PageRank. You can argue against it. That's a property of it. So where we are standing, we have 5 properties which are graph theoretical ordinal axioms. That you can, what is good now is that anyone that follows it can start and argue against them. Already there were comments, whether vote by committee is good or not. Whether other axiom I mentioned proxy is good or not. That's the only issue. We can understand these axioms. And now we can start and argue. So where do mathematics help? First of all, there is soundness. The PageRank ranking system satisfies these properties. So that's an exercise in linear algebra. A bit lengthy, but it satisfies. So we started with properties that one can argue about, but are satisfied by PageRank. And the question, of course, the big question, is whether we have a computation theorem, if we have completeness. The question arises where PageRank is the only ranking system to satisfy this axiom, because I can have zillions of systems to satisfy this axiom, so what? And the theorem that we have here is that following one. Any ranking system that satisfies isomorphism, self-edge, vote by committee, collapsing, and proxy is the PageRank ranking system. So what do we mean by that? Here are 5 axioms. If I'm excited, then I'm still excited by the result. 5 axioms, graph theoretic ordinal axioms. Didn't do any numeric computation. And what we say now is, look, it's satisfied by PageRank. You love it, you hate them. If you love them, you are stuck with PageRank. If you don't love one of them, PageRank is not your system. This is a representation theorem. This is the meaning of representation theorem. It turns out to be highly more complicated than the social science kind of thing, like for majority, but it's the same kind of role. It says, this is the essence of PageRank, in my opinion. This is the way the axiomatic approach helps us here. Now, if you are a practitioner, take these ones and use them. If you like to have another ranking system, like hubs and authorities, then we have another representation theorem for it.
So you can deal with a bipartite graph also, because hubs and authorities I think of as being, and you didn't seem to have a bipartite graph.
No, if you give a restriction on your model, then you need another representation theorem. Now, one thing to notice here, that's a remark of technicalities. The truth is, the more that you restrict the setting, the more complex are the results to obtain, because the hard part becomes harder. The part that, so we talk about bipartite graph also. Sorry? Okay, so that was the next slide. This particular result, there's a reason that I presented it here today. We have many representation theorem here. For this one, as stated here, that's the only one that I'll present here today that we don't know to prove independence of the axioms. And the reason that I mention it, because I think it's horribly hard. And I think now I even say, after a lot of time looking at it, I believe there may be dependent. But if you look at the lemmas that we prove, I open it already. So it tells us a lot. It tells us a lot. other representation here that I'll mention here today will be also have these properties. I started with it just to make the remark, basically. That's really cute, perhaps. It captures PageRank, but if you like to have independence, you still have some problem. I can cheat you a little bit and move a little bit with the definition. Other systems will have it, but for this one, this particular axioms, we don't have it. Open problems are also always good. So the question now, how much time I have in general? But when I need to finish. So I have a lot of stuff. The question is whether to go over something like a proof. Look, the whole of thing, let me put it away. In the speed that I speak now, and the nature of survey, it will take until around 2:30. The only thing here that I'd like to show you something about proof. So and just sketch even of.
Well, like 2:40, would that give you time for a sketch of a proof?
There will be many proofs. I like to give you just the idea here.
Yeah.
In order to prove completeness, they're sure without the complexity, it's not that trivial to find it. We don't use the properties themselves. We use things that are implied by these properties, which we call weak deletion, strong deletion, or duplication. Again, I don't know, I don't like to lose you. Again, wave your hands if it's too fast. The weak deletion property basically allows to remove a vertex that has both an in degree and out degree of 1. If you have something like that, that can be seen. Although everything here requires proof, it's amazing to see how it's the intuitive thing. Strong deletion is an extension of the proxy, allowing removal of a vertex with m sets of t equal predecessor and t successor. So you have
What do you mean by equal predecessor?
all of the definition is basically is comparing two ranking systems. It says if you had a ranking system, it defines all graphs that rank these guys equally and rank this guy equally when they moved here, then in a ranking system that you don't have, this guy, the ranking will remain the same. All of this comparing two systems. This is the idea. This is the algebraic way to look at it. So it basically says, look, now you can take one from each and make this kind of connection.
So you mean the projection without x of the left side will give you the ranking on the right side?
No. This is a property that holds, which means if you have a situation where a system ranks these guys similarly and these guys similarly, now and you have this x and it ranked any other way here, if you drop out this x, a ranking system that satisfies our previous axioms will also have the property that if you take a system that gets one from here and one from here, one from here and one from here, you have such one-to-one mapping, the ranking will remain as before.
So this is implied by your 5
It's not immediate. You shouldn't be able to see it.
No.
It's fine. It's a property that we use. And the last one is duplication. The duplication, which is different to vote by committee. And by the way, it's more even related to what Jennifer mentioned before. The duplicate property allows duplication of an agent successor by any factor, which means if you have here two vertices, then you can duplicate everything, assuming that you duplicate everything. Each one of them is duplicated here by a factor of 3. So instead of having this one, we have 3 agents that point the same. And here you have another, you have 3 agents that put the same. Then again, it will not change the ordering. Again, these are properties that one should prove. In fact, this is something if someone you decide to look at the proof, it's good to know these lemmas because some of these are not trivial and it is needed in order to talk about independence. So these lemmas you don't need to read carefully. Just say these properties that I mentioned are true. This is what I say. So the reason that I wanted to say something about the proof is not just because I'm excited it is the only one, because the completeness proof is constructive. So the idea is as follows. Let me wave my hands and then I'll decided not to go that much on that. So the idea is as follows. We in fact give a grossly inefficient algorithm to compute PageRank. You take a graph, you take 2 nodes, and then you manipulate this graph using the axioms. You move from one graph to another graph, where basically the rank of A and B should remain the same according to the axioms, but the graph is smaller in a sense. We drop nodes until you get to a particular situation where the ordering of A and B are the only one in the graph, and their ordering is fully determined. And since PageRank satisfy these axioms, this means this PageRank is the only one that satisfies this, because
Is it hard to prove that you can keep getting rid of nodes? Because I mean, it's not a priori clear.
no, it's nothing is clear.
5 axioms
nothing
would
is clear.
allow you to go down.
No, nothing is clear. So you go down and you get, perhaps I'll show some graphs. This was a request from Alon to do this. It's good. So the idea is that it's proof of completeness or representation by uniqueness. This is the thing. You say, look, PageRank satisfies them, but these reductions show you that the ordering of A and B is unique. And therefore you get the result. So how it looks like, just the picture, not to impress you, you can look at this. It's prepared to a longer kind of talk, to be honest, but just to show how it works. We start with the original graph, and then we start to manipulate it. So I'm just reading you to the slides. We like to look at A and B, so we added vertex on each edge, each vertex like that. And then we say, okay, by the edge deletion property, A and B should be ranked similarly. Nothing changed here in the ranking. And then we say, look, let's do some more operation. Let's, an example, let's duplicate the number of successors that A and B has. And by a factor of 3. Again, I don't like to cheat a little. I hate this. So we use another property and we change the graph. And then we can use the strong deletion property and make it to another graph. So at the end, what happens, as I say, this is not trivial, we got rid of C. We got rid of C. And now you can do the same with D or whatever until you get, again, everything requires proof, to such a situation where A and B are the only ones and there are nodes polling edges with vertices of them pointing from A to A, from B to B, and from A to B to B to A. And then basically what you do is equalize the number of edges with vertices from A to B to the number of edges with vertices from B to A by duplicating the number of edges with vertices from B and A and vice versa. And you get a situation where the number of edges here is equal to the number of edges here. And then you can just look at the graph, basically, and assume it out of generality that B has fewer self-edges. Then you add self-edges with vertices to B until A and B have the same number of self-edges. So until both of these are isomorphic, and then you should say, if you haven't added the edges, they had to be equal. But you added the edges. So one of them needs to be stronger than the others. Wow, this was fast. This was a sketch of a sketch of a sketch. But the idea is basically here, I communicate the idea that you do these manipulations and you need to prove that the axioms are kept, all of this, until you get to something which is unique over that. So this was an illustration of the descriptive approach. But now I become even, if you look at it as a criticism, you say, okay, you guys using, you personally, many guys use PageRank or things like random walk. So what are the properties behind this? And in we really capture the essence. These are the axioms, and we should, do you like it or not? But the normative approach, following the idea of error, say, look, let's start from scratch. I don't know why PageRank. Let's start and see, write axioms or requirements that we like, minimal axioms that we like that be satisfied, and see whether we can satisfy them, which is the idea in the normative approach. So the idea here, what really makes a ranking system be different than the social choice setting, is what we call now transitive effects. The idea is that the votes, the rank of your voters, should affect yours. It's not the case that you just vote for someone. You might have voted for Uri or voted for Yossi. There is an indirect effect from me to Yossi. This is something that should be captured in the system. So here are two obvious things. One can think they're obvious. So if you say, look at this guy, he's stronger as this guy, and this guy is even stronger than the other guy, though this guy should be ranked higher than this guy. Or here, this guy is as strong as this guy is as strong as this guy, but you have an additional guy. So now this guy should be stronger than the other guy. Okay? And in fact, you can formalize it if you like math. So it's defined formally. Again, it's easy to define it. We define a predecessor set of px of x as being weaker than py as the existence of one-to-one mapping between px and py, where every vertex in Px is mapped to a stronger or equal vertex in Py. Moreover, Px is strictly weaker if at least one of the comparison is strict or the mapping is not onto. This is just a long way to say the things that we just illustrated before. And what will be the requirement is called strong transitivity. A ranking system satisfies strong transitivity if for every two vertices x and y, where f ranks x predecessor set Px weaker than predecessors of y, then f must rank x weaker than y. And similarly for the strictly. Yeah.
What do you mean by stronger? Because you are not assigning number, you are assigning rank.
Right, just rank. Everything is ordinal.
No, but you remove that guy and put a stronger guy because you are not comparing them.
No. You get into situation. Stronger transitivity say, look, I created a ranking. Look at it as you created a ranking. And ordinal, everything should be ordinal. And in fact, we make it explicit in a minute. And you say, look, you created a situation where one guy, that's a preference relation, is stronger than this group of voters in the ordinal sense defined here.
In the previous picture, you removed that person from there.
You didn't remove, it's two different persons.
Two different persons.
There's already
No, he's just saying that the second voter on the left voter is stronger for the blue guy than for the green guy.
There are 6 persons.
6 persons here in this.
And you happen to rank some of them equal and one less, the yellow one less. Then you are obliged to rank the purple one more higher.
This is all ordinal, and we make this requirement explicit in a minute.
Where do you have this previous stronger, weaker comparison from? I mean, how do you have a previous ranking that you already?
No. That's a requirement. That's a good question because this teaches the axiomatic approach in a sense. I need to produce a ranking. This is a property of the ranking that I require. Like I can require a thing to be associative. I see, now I require something that I define now as transitivity. They say a ranking will be proper if it satisfies this kind of thing. Okay? That's a constraint. That's a constraint. That's not an algorithm. That's
now the ranking as a whole and the graph.
It's an outcome of the ranking.
Okay.
That's not, nothing here is algorithmic. Nothing here is like the logic, the axiomatic that appears.
Is it clear in this example in the top one that if the green, can you just put it?
Yeah.
If the
Amazing, this animation kills me. Yeah. I'm also bad in colors.
green
What
one
you say to the left?
is stronger, is rank higher than the left orange one, then why the purple
I
one
didn't
should be-
understand. You get
No, what he's saying is that if the things on the bottom, he's saying on the basis of the orangish guys who are doing the ranking, the blue guy, if those were the only ones doing the ranking, the blue guy would have to be higher.
They are not ranked themselves?
no everything you want to be. Yeah.
Well, they're ranked and that makes them bigger.
If the three
You
What
have a graph. You have a graph
What
with
at
n
what
numbers.
is the relation between the green and the orange? Why? I mean, is it?
I don't care
It
that.
doesn't
But
say anything about the
I don't care about. I
It
just give a
says if
constraint.
somebody of
See?
page rank 10 and somebody of page rank, let's
the
say 10
inequality
is-
only talks about the purple and green. It says nothing about
But
It's a very
the orange, he's
soft.
assuming he has stronger guys on the right than on the left.
Yossi, to your question, this doesn't mean anything. That can be very strong, very small. You can visit the factor. The relationships between them
You
should be
don't
the same.
compare them between themselves. You don't compare.
This
the
doesn't
orange
say
and
anything
the-
about these guys.
The orange are given.
I'll give
The
them.
orange are given.
You can scale them down.
Right.
This can be two small guys, and this a small guy, and even a smaller guy. This is, okay, that's a minimal requirement. And what is nice is this, you take it in Microsoft theory group, that's like, everyone is convinced that it's a good requirement. By the way, this is the way that I started this research. And first of all, this is to Yossi and others. Strong transitivity doesn't always apply in a sense, it doesn't restrict us too much. It doesn't say anything about this.
Well, they're not personally,
Yeah.
but they're not in the same.
Yeah, and they don't say anything about this. It's just a constraint. But if you think that is great, and I thought it's great, and I worked for a lot of time to make a system that satisfied that, here is something, it's amazing that they gave this talk at Google, and they don't ask you immediately. So, sorry for all of the names, no. So, let's assume for a minute that Yahoo and Microsoft are ranked similarly. And this is a Yahoo point to my homepage, and Microsoft point to MSN homepage. So basically, strong transitivity will mean that my homepage and MSN homepage would be ranked similarly.
If nothing else points to either.
Okay, right. Now, let's look at the following situation. That's what the requirement says currently. What we like to add is exactly what you point. But let's assume that Microsoft point only to MSN homepage. And Yahoo points the directory that points the zillions of pages happen to mention some Moshes there. Then in this case, I would say that they shouldn't be ranked the same. So, and by the way, there are people that argue that it's not the case. But if you talk about this, we need to look at weaker notions, such as weak transitivity. Again, it depends if we're looking for impossibility or possibility theorem, and we like to be honest with ourselves. But if you like to say something is impossible or whatever, we like to look at weaker transitivity. I'll take something very weak. In the one-to-one mapping, only match predecessors with equal arc degree. So, of course, you can massage it even, but only match predecessors with equal arc degree.
I'm not sure that that implication was warranted, though, because you said that if F ranks the predecessors strictly weaker than the of X strictly weaker than the predecessors of Y, then F must rank X.
It goes both directions. So you get inequality in two directions. If it's ranked X you have greater or equal in both directions.
That Yahoo points to
It works.
And the only page
It's greater or equal in both directions.
Okay, fair enough.
Okay.
What should be the answer in the...
So he's saying you dilute your authority by pointing to everybody.
Yeah.
Right? If I'm a restaurant reviewer and I say that every restaurant that I go to is great, it means less than if I'm also a great reviewer, but I say that only your restaurant is great.
But maybe then you have some hidden if you're only
We'll talk about this. I just gave an axiom. Look, I am here the math guy.
Sure. Well, whatever your ranking system is, there are going to be people who
We'll talk about this. Believe me, I can have a whole talk on that, just on this topic that you mentioned. So first of all, PageRank, good news to the not Google guys. I didn't know, satisfy weak transitivity, but not strong transitivity. Now, on the other hand, there are some stupid guys that work very hard to satisfy the non-trivial ranking system, which satisfies strong transitivity. That
is
if you were
constructive proof?
Constructive, everything is constructive. So, but I'd like to have one more requirement. And again, in the limited time that I have, I really, even with the 240.
But it's obvious that PageRank satisfies only transitivity because you're a random walk. So
Sure. So what we'd like to add, so this is what you need to remember. Weak transitivity is really weak. It's really weak. Weak transitivity is really weak. It requires very little, let's just say. Now, formally, we need to require what we mean by ordinality. And again, this is defined by a notion that is called ranked IIA. So this is meant especially to people that know classical social choice, but I'll explain to you anyway. So the idea is as follows. How we formalize ordinality? It's called, we put here a system. An agent with votes from two weak agents should be ranked the same as one with a vote from one strong agent. I'm not saying this is true. I'm just saying that we'd like to be consistent. What I mean by that? Just a minute. Wow. I'm speaking loud. What to do with my time? So look at this graph. At this graph, look at these two agents. These two agents point to this guy. They are weak in a sense. And this is stronger that put it to this guy. And these guys are ranked the same. So it's consistent with this statement. Now, this guy, here are two weak guys that point to this guy, and one strong guy to put to this guy. So we are consistent with this statement. On the other hand, if here we have two weak guys, and here we have strong guy, it's ranked the same, so we are not consistent with this statement. So the idea basically is to require consistency. What do we mean by that? We say, look at two nodes, A and B. There are a bunch of voters that vote for A, a bunch of voters that vote for B. Look at all of the binary relationships between them. This should be uniquely, in a consistent way, defined who will be ranked higher, A or B. So this is not a right statement, but we'd like to be consistent with some statement. So we cannot be in a situation to say, look, here are two guys that pointed to me, and one strong guys that pointed to you, and I'm ranked lower than you, while in another place in the graph, you behave completely differently. So this is, you can call it consistency. But it's called ranked IIA in order to distinguish between error IIA. So basically this is what we have. it can be seen in the ordinality requirement. So
Okay, so that's your IIA.
that's the IIA. So we have basically just two axioms. So those of you who know a little bit mathematics or social sciences, we have really little. We have dichotomous preferences, like a graph, and we have weak transitivity that no one will argue, that minimal amount of transitivity the one will ask in a system where you have such rank, and we have consistency or independence of relative alternatives, and we have the following theorem. Let's start with the positive, negative sign. There exists no general ranking system that satisfies weak transitivity at rank IA. And the proof is constructive, and it will be left to the people that will stay after 240, because I have illustration, because I have more important things to show. What I'd like to show, because people ask me many questions, so I like to kill all of the questions. So this is the illustration that you missed, thanks to Alon. I cannot do that. Our possibility result exists in very limited settings. For small graphs, strongly connected graphs, bipartite graph, based on request from a company that you can imagine what it is. Single vote per agent. And the proofs are more complex. But we have impossibility here. So, okay, but here, let me play to be more the positive guy. So what I'm saying now, because I came and sold to you guys an axiomatic approach, and then I say, here are some axioms, I'll give you a new system, and then I show impossibility. Another thing that we'll talk to guys which are practitioners will throw you away. So you have shown me impossibility. So I like the impossibility, but perhaps there is something inherent there in the consistency on dependent alternatives and transitivity that doesn't allow such things to happen together, so we proved it, so what? So it's interesting to notice that under a very slightly different notion of transitivity, these properties can be satisfied together. Moreover, the proposed ranking system is non-trivial and interesting, and even have some nice number theory in a sense into it, not deep one. So basically, we call it quasi transitivity. Basically, to make a long story short, it requires in this situation just greater or equal. He says, in this situation, you have a strong guy, two strong guys, so let's believe the strong guy. I don't know. Just greater or equal. You need to be careful, because in this situation, I didn't define it formally, the trivial ranking system that rank everyone similarly may suddenly be applicable, so you may need to make an explicit requirement that we don't allow the trivial system. And it turns out that this requirement is really natural and nice, and we can satisfy it with this. So there exists a non-trivial ranking system satisfying rank A in quasi transitivity. I'll say a word about this. I'm tempted. So I'm waving my hands, but the idea is as follows. The idea is that you start and rank. It's constructive. You start and rank based on the in degree. And now think about it as a number, as a number written on the basis of the number of nodes plus 1. So the first digit, the most significant digit, is the in degree. And then you like to take the maximum number that will be associated with your predecessors. And the problem is that there are loops. But when you get to loops, you take the periodic number associated with this loop. So, of course, this is when ring. I need to show you that it's a fixed point there, that it's stabilized, that it's a good ranking system, that it satisfies. And this is we can do, but just to illustrate to you, perhaps, if it helps, how it works, how functionally, how it works. So we need to associate a value with this guy. So it will be 0.3 x. I don't know what will be the predecessor, so we go recursively to the predecessors. And this is 0 because it has no, well, this is just my eyes, or yeah, I'm colorblind, that's fine. There is 0 there. And this guy is 0.1. Why? Because this is another predecessor, and it has just predecessor of value 0, so its value is already determined. And this is 1.x because its value is not determined. I'd like bear with me with 1 or 2 of this. And this is 1.x because it has predecessor of the in degree of 1. And this has in degree of 2. Sorry, this down. But look what happens now. Suddenly, this is a predecessor of this guy. So which number we'll associate here? So the number that is associated here is 112, 112, 112, 112 periodically. And we continue that way, recursive way, that Again, we'll say after 245. So we get here a bunch of numbers that really I described to you the algorithm, but I need to prove to you, of course, that first of all, it stops, it's fine, it satisfies our axioms. It's a non-trivial ranking system, and to be honest, we also implemented it in a particular kind of setting, and it leads to indeed interesting results. So we have possibility results too.
Is it unique or is it?
No.
Does it depend on which way you run?
Oh, the ranking is unique. The ranking is unique. Sure. Yeah, good question. Thanks. Okay, so what I need to present in the 15 minutes left, a choice, and I've already made the choice. One of them is talk about incentive compatible ranking systems, and one is the personalized ranking system. I say a word on incentive compatible, because we have 2 papers written on them that I invite you to look at. The idea is basically that agents may choose to cheat and not report their real preferences in order to improve their position. Now, utility of agents only depends on their own rank in our system, but not on the rank of other agents, and it's non-increasing in rank. This is all that we assume. We have a special rule for ties, but basically, that's all that we assume. By the way, notice that incentive compatibility here, I know that there are people that know mechanism design, is a very different thing than in context of mechanism design. Here, in mechanism design, the issue is that we don't know the type of the agent. We don't know its preference relation. Here we do know the preference relation. We like to be ranked first. The only thing he likes to manipulate. So the notion of incentive compatibility that I've chosen to just to mention here is that if you have 2 graphs, G and G prime, that differ only in the outgoing edges from vertex V, then the ranking system is strongly incentive compatible if for every utility function you have that such manipulation will not change the rank of V. Now, here I'm cheating in order not to cheat, which means our results are much stronger than that, the method I mentioned. Here I talk about out-degree manipulation. There is another famous kind of manipulation, which is siblings, creating copies of yourself. Everything that I'll say from this point on holds for, because I didn't look at the definition, for the question where you can manipulate both your out-degree and the fact that you have more siblings. For good and for bad, the results will remain the same. So to sum in one slide, these 2 things, here is the punchline. We have classified several types of incentive compatible ranking system under a wide range of axioms. What do you mean? From the mathematics perspective, we write certain axioms, and we say whether any ranking system that works with this axiom can be incentive compatible. But from the practical perspective, this is the truth. The classification has shown that full incentive compatibility is impossible for any practical purpose. It's very nice to see our artificial ranking systems, which are incentive compatible. We are very happy with them, but they're not useful. What is more interesting, we have also quantified the incentive compatibility of non-ranking systems and suggested some new ranking systems that are almost incentive compatible. The reason that I skip it is that there are many definitions of what we mean here by almost. Almost by means of worst case, how much you can manipulate by rank, by average, by the number of agents that can manipulate. There are a bunch of many results that are hidden behind these naive things that I'm telling you, like this marketing pitch. There are many things to say here, but basically we can also, for example, in PageRank, we, and practically alone, even in practice, I can show you the software, can manipulate half of the internet. In the sense, if you are PageRank and you are somewhere here, you can move somewhere else. And it doesn't help you that the internet has small world properties and stuff like that. But for other systems, you cannot do that. So this is the right statement. And due to lack of time, this was done. Okay. So what I'd like to do towards the end of this talk is to concentrate on this. Why? Because I'd like to sell you some concepts here, if you didn't notice. And one of these here, if this was a deviation from the classical total choice, with all of the respect to it, by having a set of agents instead of technical inside, now I'd like to make another deviation. And this has to do with personalization. I'd like to, in trust system, for example, and we live and breathe them, the client of the ranking system is a participant. So we have all of these social networks and e-commerce sites and all of this kind of thing where basically it's useful to generate a personalized ranking for each individual. Who cares about the general ranking? It's good for page ranking, perhaps. But in a trust system, like in opinions, I say we are trust, you say who do you trust. And now what I'd like to know something about the trust of the people in this, who to trust more. So nice thing here from the practical thing that many impossibility results are reversed. So let's start. 10 minutes for that. So a personal ranking system is like a general ranking system, but there is additional parameter which we call the source, the agent on whose perspective we are ranking. Now, in this talk, we define it only in graphs where the source is a root. There is a directed path from S to all vertices, and I even assumed our assumption that it's strongly connected. It can really be removed. I just don't like to have on the slide something written which is wrong. It needs some technical patches, so assume that the graph is strongly connected. This is not a major issue for us. So we have a strongly connected graph. You like to rank from the perspective of each node to know what is a good ranking system. So examples that will be more concrete. One of them, very famous, is the distance rule. Rank agents based on the length of shortest path from S. Closer agents are to you, the better they are. And this is exactly defined that way. There is a very famous system, personalized PageRank, with damping factor D, the PageRank procedure with probability D of which starting at vertex S. Very popular system. So it gives more weight to the source. Alpha rank that we invented, again, one needs to define as our system that it's even a ranking system because it's built on fixed point. So that's rank based on fixed point value when every vertex is valued at alpha times the sum of its predecessor's value, and S is defined as 1 over n, as 1, where alpha is 1 over n squared. Oh, that's horrible. Let me explain what is going on here. So the idea you will see in a minute why we like.
Weight of 1 to the root, and then you go.
Yeah, the root like need to be the closest one, the strongest one. So we define a fixed point that we say every node is alpha times the sum of its predecessors. Okay? This gives us a refinement of the distance rule if you take it alpha to be small enough, such as 1 over n squared, where n is the number of the vertices. And it has a nice property that I'll mention in a minute. Anyway, just illustration, the distance rule here will rank, let's put all of this, A as B, C as D, and E as F. So this is just distance. Alpha rank is slightly more sophisticated. It will notice in a sense that B should be ranked in a sense higher than A because also A point to B and not only S. Again, this is not something good to say in the system. Soon we'll talk about the axiomatic thing. Personalized PageRank, just to notice, those people that like personalized PageRank, with certain damping factors, suddenly S will not be ranked first, something that is not nice. Usually the system like to assume that you believe in yourself, so you are the most trusted one. In other cases, it gets some output. Anyway, this is just system, but what I want to sell to you, as you already know, is the axiomatic approach. So there is now something that we should have, self-confidence, that all system people think is good if the source S is ranked stronger than all other vertices. But other than that, all of the requirements that we mentioned before make perfect sense. All of this notion of strong, quasi-weak transitivity, this consistency like ranked A, the strong incentive compatibility. So, to those of you that lost me, what does this say? This means that we like to have transitive effects. This means we like to be consistent. This means that we don't like people to cheat. And these are like the 3 ingredients that we start with. And it would be nice if you know what kind of trust system satisfies this. In fact, what we use, following again many reading in very informal literature, which is amazing, what people really like in trust systems is what I call now strong quasi-transitivity. I need to make you some order with all of the transitivity. That basically says that in this case, where this guy is stronger than this guy, and this guy is really stronger than this guy, we'd like to prefer this to that. So that's just not to cheat you. But anyway, let's remain where we are. When I talk about transitivity, I talk about minimal effects like that, transitive effects like that.
That makes it harder to cheat, that you make that
Maybe.
inequality not strict on
We'll talk.
Because if you create an extra person,
You're
doesn't
right.
necessarily
You're
help.
right. You're right. But we'll talk but not that. We'll talk about full characterization in a minute. But the idea is you'd like to have transitive effects. You have relative there's consistency, which is called relative rank independence of irrelevant alternatives, and we'd like to have incentive compatibility. So let's keep this a summary, not of the whole talk, but all of something about the results that were mentioned in the previous slide. If you look at it, just as a warm-up, distance satisfies ranked IIA, incentive compatibility, and strong quasi-transitivity, satisfy everything. Personalized PageRank, which is very loved, doesn't satisfy anything. And alpha rank that we love, or soon you'll see that it's something that you love more, is not incentive compatible, is not ranked IIA, but it's strong transitive compatibility.
By distance, you mean just
pure distance. That, yeah, yeah. And by the way, we didn't like it. All of the systems we did like say, look, it's not allowed you to refine things a little bit. So what is basically the big question, mathematically speaking, but also practically speaking? The real question is, what do we have here? If I can characterize to you exactly what you have here, I'll be happy. And so this will be done in the coming minutes. So I'll be slow and throw at me stones if it's a. So I'll first define a system that I call strong count system. What is this? It sets S to be the top ranked vertex and basically ranks by comparing the strongest predecessors. If you look at distance, what distance does? It basically defines your place according to the strongest predecessor. This is basically distance. But the idea here is, look at your strongest predecessor. There may be a situation that the strongest predecessor that I have and the strongest predecessor that we have are the same. In this case, strong count say, count the number of strongest predecessors that I have and we have, and I'll be ranked higher if I have a larger number of stronger predecessors. This is a strong count, and it's easy to see that it satisfies these requirements. Let's step back. Let's go a step forward. This is generalized strong count. Now we define to you a family of ranking system. What is this? Again, waving my hands. It defines first the source. Then it looks at the strongest predecessor. If there are ties, it uses a non-decreasing function on the number of stronger predecessors. What I mean by that? It says, look, it may be the case that a system consider 1 and 2 strong votes as equivalent and consider 3 or more strong votes as equivalent but strictly stronger. So I mean, let's assume that my strongest predecessor or Jennifer's strongest predecessor is 9. But I have 1 and you have 2. So I consider that 1 and 2 are equivalent according to this fraction. But if you had 3, it were more than that. So there are like intervals. Like we say, there is a non-decreasing function over the natural numbers that define to you when to distinguish between the number of strongest predecessors. This is what we call a generalized strong count system. And here as a result, I was excited in this talk several times. This is the third time, and I'm really still excited about this one. This gives you really the story what is in the middle. A personal ranking system, self-confidence, strong quasi-transitivity, ranked IIA, strong incentive compatible, all of these nice things, if and only if it's a generalized strong count system. So it means if you like to be consistent, to have transitive effects, and you like to have no cheating, that's all you have. Choose among these. Now, the question here, all of these requirements are essential. All axioms are required for the previous result. If we relax any axiom, we don't get it. And the reason that I mentioned it is just because if we relax some of the axiom, we still will manage to find very interesting ranking system that I like to mention to you very briefly, but it will not satisfy all of them. For example, the artificial systems that will satisfy no self-confidence, or that will not strong quasi-transitive. But there are other interesting systems, such as the path count personalized ranking system. By the way, the only thing that is computationally impossible here, other things you can really implement. This rank vertices based on distance, breaking ties by the number of shortest directed path each vertex has from the source. Believe me, it was hard to get into it. So the idea of this example satisfies everything, excluding consistency. On the other hand, these systems with the numbers that I've shown you before that, the recursive in-degree ranking system, can be adapted to personalized setting by giving the source vertex a maximal value, like it was n plus 1, like it's the strongest one, and then we just apply the same algorithm, And now it satisfies everything, but not the selective compatibility.
Do you have one where you take away self-confidence?
Yeah, that's easy. Personalized PageRank.
I see, but I wonder sometimes, like, I might not be that self-confident if I don't know anything. If I go into a situation, I might say, well, I've only gathered a certain amount of data, so I actually, for a while at least, until I gather enough data, do trust somebody else more than I trust
So
myself.
you asked me a question, I need to think about it. And the question that you ask that's good, because now we can sum up what is the axiomatic approach. If you believe, yes, we have. You have, I already know. But you say, look, I don't like to have crazy system, personalized PageRank people like. I'd like to remove only this, but really be able to satisfy all of the rest, and we have such a system. So we say, you'd like still to have incentive compatible, to have rank IA, to have strong quasi transitivity, but not self-confidence. What we don't have, it's a nice research problem to characterize all of the systems that have these properties. So,
or at least, something like your function where there were like jumps in self-confidence or something. I've gathered enough data for a while.
Yeah, that's for me the full characterization.
Somebody else, and now I've gathered enough data. Now my self-confidence jumps or something. Yeah.
okay. So the summary, those are pictures that theoreticians like, that everything is full. Says, look, these are the basic three requirements, these three worlds. Transitive effects, consistency, incentive compatibility. We know exactly what is in the middle. We know what appears everywhere. And we even managed to mention things which are even interesting that appear in the middle. Yeah?
I'm a little bit confused. I thought a moment ago that you said that personalized PageRank is something that will satisfy strong quasi, basically everything except self-confidence requirement.
No. Personalized PageRank will not satisfy anything. This was written in, we have it here.
Yeah, I was looking for what you're saying, just throughout this.
Jennifer wanted to hear, personal PageRank could just appear here like, personal.
You're saying it doesn't satisfy any.
Yeah, this is the.
Yeah, personalized PageRank doesn't satisfy anything.
Okay.
I was asking for something which just didn't satisfy self-confidence, but satisfied all the other three.
And exactly, these are the questions that I like, to be frank, is because when I like, because I say, look, I sold to you already the axiomatic approach, which means, okay. So let me sum up and then say something in addition. So that's a very quick summary, just very technical. These are the things that I'm proud of, technically speaking. We have shown a proven representation theorem of PageRank that turns out to be highly non-trivial. And I refer mainly to the theorem that I mentioned you today because there are others that are cleaner even. But here are dirty, but they really tell you something about PageRank. We have shown a normative approach. We have seen both impossibility and possibility results. In fact, here the reason to be proud, to be frank, came several weeks ago when I talked with a guy from a very big company working on ranking system, and I'm showing the possibility results in the graph. And he was a theoretician. He said, oh, for this graph, we have a special treatment. And then I realized that impossibility results make sense. So somehow the impossibility results found the graph that have special treatment that cannot be handled. Also, possibility results were what is important here. The results are constructive. We have new ranking systems. We have applied this approach to personalized ranking systems, and their results are very positive. And on the conceptual side, there are many issues open. Anyone that like to join this research? Many questions, many kind of things. What I want to tell you is, I'll be extreme. I think that the only way to evaluate ranking systems is the axiomatic approach. I've seen everything which are leave one out kind of thing. We don't know what the user have in mind. And what is nice in this setting, indifferent to many things in mechanism design and other settings, I don't care. I'm saying I'm starting like a real computer programmer. And I say something very rigorous. This is what I'd like to happen. Here is your ranking system. It's very different what people have been doing there before, but I think it can really work. One can claim what you do here, how it works computationally. All of the systems here are computationally easy, excluding one. The only thing here also to mention is that when Yahoo or Google or Microsoft introduce a new ranking system, it introduces one. So does it mean that if you like to, and this is also an exercise that we have done based on some requests, if you look interested also in click-throughs, not just in links, So we need another representation theorem, but you can do that if you have the expertise that we have, like, verification of problems someone have. We do it manually. We really find to you the axiomatic approach, and then you can love it or hate it, and then we'll see. So this really scales in a sense that you don't implement we cannot do it for any tweak that the programming will do, but we can do it over the essential of the ranking system. So I'm anything in further research, another talk, and that's important. Thank you. Yeah.
So you've got certain results which tell you that certain things are impossible. You want this and this and this, and you can't have all of them. But sometimes in certain cases, you can't have all of them on some small graphs that you can actually construct, but as the graphs get larger and larger, you just have very small violations of some of these things. There are results along those lines that Nicole has. She's no longer here, and that in some work that I did, we've got that. So I'm wondering. So it's almost as good. And when you're talking about the web with 100 billion sites, who cares if as the number of sites
Talk
goes
about
to
almost
infinity,
always.
the violation goes.
So we have
to
looked at it. We have looked at it. In fact, I mentioned it briefly and talk about incentive compatibility. In fact, we were hoping for this, like take small world properties or something which is, again, we are theoreticians, so we don't talk about specific graphs. But we know one very specific graph, and which is the internet. And we also had one other graph, because Alon is also a hacker, so we know the eBay reputation system, and we really played with them. And we can do that and measure it on them, and the same kind of results are obtained.
So you see substantial
Yeah, the only thing, we were very happy about that. And in fact, we call for joint work on these related issues. We are not, all of this. We were hoping for that. We were hoping for all of this. Currently, in what we have looked at, I would tell you, if you've had, these are the results that we can look at everything. But for example, bipartite graph were very important because people look at it as trading. So we started to talk with eBay guys or something like that, not mentioned exactly, but we say, okay, that's nice, but your system is nice, and you do many things, but we have buyers and sellers. We have bipartite graph. So we looked at that. So I cannot answer any, give me expander with.
You understand what I'm saying.
Sure.
The impossibility result doesn't bother me if the degree of impossibility goes, the degree of violation goes to zero as the graph gets larger. So it would be interesting to somehow get quantitative versions of this and show that the violations either do or don't tend to zero. And those are much harder theorems. But
No. By the way, they are not harder theorems in a sense. Let's put it that way. When you talk about representation theorems, when you have quantification, we have the number, the results are easier in a sense because you have more freedom. When we talk about incentive compatibility, we measure them. But of course, all of this thing of looking at graph families, we really not, that's really called for collaboration. You can find me we tested on some small world properties graph or stuff like that, do this theory kind of thing. But there may be some, strange expanders hidden there that for them, weak transitivity with this plus minus plus will work only, nicely. So we don't know. So we are not in this stage.
Well, if you can find a small graph that whenever it occurs in the large graph will give you a violation, then obviously it will have a density of violations and it won't go to zero. But there are certain results that it's not the small graph in the large graph that's giving it to you. And so it does go to zero.
I see. So, Thanks. More questions? Thanks again.